Okay, today I'd like to demonstrate paired programming with AI Studio by Google. And so we've got some instructions here. Use a formal and academic tone. Provide Python scripts when applicable. Um, we also are going to be working in Cursor IDE using the DeepSeek R1 model to program circuits for the IBM Quantum Cloud. So we're going to get the session started. Hello.
Greetings. I have received the two images you sent. They appear to be screenshots of a coding environment, specifically relating to quantum computing, with a markdown document on the right side describing the unitary property of the Hadamard gate. Do you have any specific questions or tasks you would like to discuss, or is there any way I can assist you?
Yeah, right now what we're doing is we're going to utilize ControlFlow to submit um, jobs to the IBM Quantum Cloud. So
Okay,
he, here we have some instructions here.
based on the images, it appears you are working with a Python script for quantum computing, and there's a markdown document outlining the unitary property of the Hadamard gate alongside it. Additionally, you've highlighted a section that includes instructions related to the prompt function. Is there anything specific you would like to discuss regarding these instructions or any other element visible on the screen?
At this time, I'd like to run the job, and I just want to have you read off the output to me.
Certainly. Based on the provided images, it appears you are preparing to execute a quantum computing job, specifically example 2, which involves cloud execution on IBM Quantum. You've highlighted the section of code that initializes the quantum circuit, applies a Hadamard gate, and then measures the qubit. You also mentioned that you would like me to read out the output. Please note that I cannot directly execute code, and therefore I am unable to run the job for you. However, after the code is executed, the output will likely consist of measurement results, potentially in the form of counts of zeros and ones, corresponding to the possible outcomes of the measurement. If you run the job and provide me with the output, I will gladly read it out to you. Do you have any further questions before you run the job? Or would you like me to elaborate on any aspect of the code?
Yeah, while we're waiting for the job to complete, looks like it was successfully submitted. Could you go ahead and just explain how the Hadamard gate is show that the Hadamard gate is unitary?
Certainly. It appears your quantum computing job has been submitted successfully, and you've received some initial output. Based on the images, here's what I can gather and explain. Job submission and backend information. Backend. The job was run on the IBM Q underscore Sherbrooke backend. Backend configuration. The backend has 127 qubits and the basis gates are MyDate RZSXX. Pending jobs. There are 3 pending jobs in the queue. Job ID. The job ID is CJMW 70C1H 000B 16AG. Job submission message. You received a confirmation message indicating that the job was submitted and that the results would take some time to complete. Raw result payload. A raw result payload is printed, which contains the measurement data in the form of bit arrays. This includes metadata such as circuit information and the version. Cloud execution results, counts. The output of the measurement is provided as a dictionary. It indicates that the measurement resulted in 0, 987, 1, 13. Explanation of Hadamard gate unitarity. On the right side of the screen, the markdown document outlines the proof that the Hadamard gate is unitary. Unitary property. A quantum gate is unitary if, when multiplied by its conjugate transpose, it results in the identity matrix. This is expressed as HH equals I. Hadamard gate matrix. The Hadamard gate is defined as a matrix with elements that are either 1 slash square root 2 or minus 1 slash square root 2. Steps to prove unitarity. 1. The Hadamard matrix is presented. 2. The conjugate transpose H is computed, which in this case is the same as H because the elements are real. 3. The multiplication H eat H is performed using the matrix multiplication rules, resulting in a 2 by 2 identity matrix. Summary. You successfully submitted a quantum job to the IBM Quantum platform using the IBM Q underscore Sherbrooke backend. The output you received indicates that after applying the Hadamard gate to a qubit initialized in the 0 state and measuring, you observed a result of 0 987 times and a result of 113 times. This is consistent with the Hadamard gate's behavior, which puts a qubit into a superposition of 0 and 1 with roughly equal probabilities. The Markdown document provides a mathematical explanation for why the Hadamard gate is considered unitary. This is a fundamental property that ensures quantum computations are reversible and preserves probabilities. Is there anything else you would like to discuss or have me clarify about this?
Actually, I do appreciate you clarifying the results of the counts here, that they're consistent with the Hadamard gate.
Sir,
And quickly, the Hadamard gate can be used to put the qubit in a state of superposition. Is that correct?
yes, that is correct. Let's break down what's happening and confirm the
Really
consistency
quick, I
you've
think
asked
our
about.
job, our program, so the IBM Quantum Cloud has sent a response. So we're done with that. So we're finally getting some results here. So it took a little bit. We were actually querying the Google Gemini API, um, that I have integrated with ControlFlow here, and we took we were passing over there the raw payload, asking for the quasi distribution result counts. Let's see what that says here. Can you read this off to me? This response from the ControlFlow.
Okay, I will read out the relevant information from the images you've sent, focusing on the output and the response from the control flow. It appears you've successfully run your quantum circuit with control flow and have received the results. Output from cloud execution counts. As before, the measurement results are displayed in a dictionary format, showing the counts for each outcome. 0, 987, 1, 13. Control flow response, LLM response. The response from the large language model, LLM, integrated with your control flow is 0, 0.29291, 0.7081.
All right, hold right there. That's actually incorrect. That's just standard theoretical values that I have set up here. They're constants. The actual output from the control flow, when it's processing the raw payload, based on the instruction set that we discussed at the beginning of the video, the is actually 0, 5,000, 1, 5,000. So that's probably more of, I want to say like a just a standard response, because I don't think it was able to process our raw payload because it didn't seem to have relevant information. So it looks like the Gemini cut out there, but that's fine. We can just restart it. Uh, and then here's all the responses from Gemini. And I'm trying to see if I can get it to write some code for us. So just really quick, I wanted to demonstrate that earlier I had said show that the Hadamard gate is unitary. I set that to DeepSeek thinking model through Cursor IDE here and on its agent or ask. And then it gave us this nicely formatted proof. And then it also gives the Python code, which I didn't even ask for. So that was pleasant. So I want to just see if I can replicate that really quick with the same question. And then I'd like to implement that Python script of it that it provided before, and also verifies the code. So let's go ahead and implement that, and we'll switch gears for the Gemini AI Studio. Okay, so let's go here. So we're sharing again. Okay, so I have some code to verify that the Hadamard gate is unitary. This is just fundamental. We're not actually doing anything with the circuits, but I'm just interested for learning. So I have some code here. Let's implement it. And do you see anything that I could probably improve upon with this code?
Certainly. Examining the provided code, several areas could be improved for clarity, efficiency, and adherence to best practices in quantum computing with Qiskit. First, the code mixes several different approaches and styles, which makes it difficult to read. For example, in the first example, you are using the Qiskit runtime service to execute on real hardware, while later examples seem to be focused on local execution and simulation. This lack of consistency reduces the clarity. Second, in several places, you are using print statements to output information about the circuits. While this is fine for debugging, in a more formal setting, you should use logging instead. This is especially relevant
You still there? Stop using ControlFlow for now.
The images provided depict a quantum computing program, specifically focusing on the Hadamard gate. The code includes several sections which will now be described in detail.
So
1.
here on
Count
lines 120 to 125, is there any operation that we could perform on the quantum circuit in order to submit it to this um, to the IBM Quantum Cloud?
based on the images. これらの画像は量子コンピュータムのプログラム、特にアダマールゲートに焦点を当てているようです。コードにはいくつかのセクションが含まれており、そのうちの1つは量子化、ロジック格子、その結果を分析するための量子、コンピューティングプラットフォームである IBM Quantum Experience をインターフェースしています。具体的には以下の操作を実行しているように見えます。1. 量子回路の初期化。まず、2の量子。ビットで構成される量子回路。QC equals これらのが像から判断すると、量子か色
Hey,
が
so
量
it
子。
sounds like
こ
you're speaking Japanese.
いい。私は日本語を話していません。私は英語で応答しています。以前の応答がもういいか日本語だった場合は申し訳ありません。何かお手伝いできることはありますか？
Wow. I don't know how to speak Japanese, but I think I could tell as I watch enough cartoons. Yeah, I'm pretty sure that's Japanese. Wow. Well, I
The
think, yeah, go ahead.
provided images show a quantum computing program focused on the Hadamard gate, similar to the previous ones. The code executes on the IBM Quantum platform. Here's what's happening in the provided images. 1. Quantum circuit initialization. A quantum circuit with 2 qubits is created. QC equals quantum circuit 2.
Hey,
2.
um, so I'm glad you're back to English. Is there any operation we can perform on the quantum circuit before we send it to the IBM Cloud?
Okay, looking at the images, before the quantum circuit is sent to the IBM Cloud, a Hadamard gate is applied to all qubits in the circuit, specifically using the command QCH. After this, a measurement is also added to the circuit with QC measure underscore all. This prepares the quantum state and sets the stage to have the results measured once the circuit has been run on a quantum computer.
How
These are
would
the only operations applied.
how would you modify this code uh, to perform more operations on the circuit before sending it to, or the qubit before sending it to the IBM Quantum Cloud? And then also, can you put the code snippets in the your chat here?
Certainly. To perform more operations on the quantum circuit before sending it to the IBM Cloud, you could add more quantum gates after the Hadamard gate and before the measurement. For example, you could add a poly-X gate, which is represented by QC.X qubit underscore index, a poly-Y gate, QCY qubit underscore index, a poly-Z gate, QCZ qubit underscore index, or a controlled NOT gate using QC.CX control underscore qubit underscore index, target underscore qubit underscore index. These would allow you to explore different quantum operations and their effects on the circuit. You can also perform rotations using QCRX angle qubit underscore index, QC.RY angle qubit underscore index, or QCRZ angle qubit underscore index. Here's an example of how you might modify the code to include a poly-X gate on the first qubit and a CNOT gate between the first and second qubit after applying the Hadamard gate and before measuring Python hash. Create a quantum circuit with 2 qubits. QC equals quantum circuit. 2. Hash. Apply a Hadamard gate to all qubits. QCH01. Hash. Add a poly X gate on the first qubit. QCX0. Hashtag gate a CNOT gate with control qubit 0 and target qubit 1. QC.CX01. Hash measure all qubits. QC.measure underscore all. Print QC. Ooh. This modified code first creates a 2-qubit quantum circuit, then applies a Hadamard gate to both qubits. After that, it applies a poly X gate to the first qubit and a CNOT gate between the first. To apply a CNOT controlled NOT gate to a quantum circuit in Python using Qiskit, you would use the CX method of the quantum circuit object. The CNOT gate is a 2-qubit gate that flips the state of the target qubit if the control qubit is in the 1 state. Here's how you can do it. Python, from Qiskit import quantum circuit, hash, create a quantum circuit with 2 qubits, QC equals quantum circuit 2. Hash, apply a CNOT gate with control qubit 0 and target qubit 1, QC.CX01. Hash, you can visualize the circuit using hash print, QC, hash QC, draw, MPL, hash if you want to draw using matplotlib. Explanation. 1. Import quantum circuit. First, import the quantum circuit class from the Qiskit library. 2. Create a quantum circuit. Create a quantum circuit with the desired number of qubits using QC equals quantum circuit, num underscore qubits. 3. Apply the CNOT gate. Apply the CNOT gate using the CX method, passing the control qubit index as the first argument and the target qubit index as the second argument. QC.CX, control underscore qubit, target underscore qubit. In this example, qubit 0 is the control and qubit 1 is the target. Remember that qubit indices start at 0. Example with Hadamard gate. Here's an example where a Hadamard gate is applied to the control qubit
So
before
here
the
we're going to go ahead
CNOT.
and it looks like we're going to apply the X gate to the quantum circuit to create the 1 state, and then we're going to apply the Hadamard gate to create superposition. And then I was just asking what the steps to compute conjugate 1.
Okay, let's break down the steps to compute the effect of the Hadamard gate on a qubit in the 1 state as shown in the images. The Hadamard gate creates a superposition by transforming the basis states. Here's how it works when applied to the 1 greater than state. Step 1. Define the basis states in the Hadamard matrix. Computational basis states. The 2 basis states for a single qubit are 0 and 1, which can be represented as column vectors. 0 equals net det Dagor anet det 1 equals 0, 1. Hadamard gate matrix, H. The Hadamard gate is represented by the following matrix. H equals 1 / square root 2, 1 minus 1. Step 2. Apply the Hadamard gate, H to 1. To apply the Hadamard gate to the 1 state, perform matrix multiplication of the Hadamard matrix by the column vector representation of 1. 1 equals 1 square root 2, 1, 1 minus 1, 0, 1. Step 3. Perform matrix multiplication. 1 equals 1 square root 2, 1, 0 plus 1, 1, 1, 0 plus minus 1, 1. 1 equals 1 square root 2 minus 1. Step 4. Final result. 1 equals 1 square root 2, 0, 1 square root 2. 1, which can also be represented as 1 equals 0, 1 square root 2. This result is a superposition of the 0 and 1 states, with a negative sign in front of the 1 state, which has to do with the phase. In summary, when you apply a Hadamard gate to the 1 state, it transforms it into an equal superposition of the 0 and 1 states, with the 1 state having a negative phase, which is sometimes represented as 0, 1 square root 2. Let me know if you'd like any further clarification or have additional questions.
Can you explain this circuit print from the operations that we performed here, displayed in the terminal?
Certainly, let's discuss the print, QC, and QC draw operations in the context of quantum circuits using Qiskit and how they display the circuit. Print, QC. When you use print, QC, Qiskit provides a text-based representation of your quantum circuit in a format that shows the sequence of operations. The text output is useful for debugging and quickly checking the structure of the circuit. In the images, print, QC, outputs something like I
So the
Q underscore 0.
so this looks correct. You got the
I
X
Q underscore 1.
X gate,
X.
and then the Hadamard gate.
It shows that the circuit has two qubits, Q underscore 0 and Q underscore 1. The first qubit has a Hadamard gate applied,
So it doesn't
then
look
a
like
control is
the.
applied, where the target is the second qubit where an X gate is applied. QC draw. That
So it
is,
doesn't look
the
like.
QC draw method provides a visual
Excuse me.
representation of the circuit in the form of a diagram. This
I
diagram
guess it's.
illustrates the qubits as horizontal lines and
Just
the
gonna
quantum
wait
gates as
till it
boxes or
finishes.
symbols. This is often easier to grasp than the text-based output, especially when dealing with
Oh, it's just I'm not even actually talking to it. It's just playing back. Okay, let's start over. Okay, it looks like our operations were successful. We applied the X gate and then we applied the Hadamard gate, and that's shown in our output with the draw.
based on
But we did get an error when we submitted the job to IBM Cloud. This instruction on qubit 0 is not supported by the target system. So
it,
I'm not sure if the quantum circuit being in this assignment here of 1-1, I've only been able to get it to work with the 1.
based on the images, it appears you are working with a quantum computing environment, likely using IBM's Qiskit. You've created a quantum circuit, applied a Hadamard gate, and measured the qubit. However, there seems to be an error related to the instruction set not being supported by the target system. This is likely due to a limitation of the specific quantum hardware you are attempting to run your code on.
Mm-hmm.
You also mentioned it appears that you're encountering an error with your quantum circuit execution on IBM Quantum. Specifically, the error message indicates error connecting to IBM Quantum circuit.measure, missing one required positional argument, qubit. It seems that you're calling the measure function without specifying which qubit to measure. Additionally, it seems like there might be an issue with your authentication, as the warning suggests that you must have valid credentials set using ibmq.save_account,
No,
and the backend has.
that's something we put into the output for the print, so you can ignore that.
Okay, I see that you're encountering a new error. It seems like you're now getting an index error. Index 0 is out of range for size 0 inches when trying to access the results of the quantum circuit execution. This error typically arises when you try to access an element of a list or array at an index that doesn't exist because the list is empty. This could mean that the measurement is not producing any results. Also, I see the previous error connecting to IBM Quantum message and that the AP key might not be properly set, meaning that you might not be able to send jobs to IBM Quantum, which would explain why no results are being produced. It might be worth checking that your authentication with IBM Quantum is working correctly.
So I just decided to use measure all here. So we
Okay,
are getting an error again. Yeah, it's not supported by the target
it's,
system. So I guess we need to change the backend system instead of choosing, least busy.
it appears you've made some progress in your quantum computing workflow. You've changed the QC.measure 0 to QC.measure_all and are now encountering a new error message. The instruction H on qubits 0 is not supported by the target system. This message indicates that the specific quantum hardware you are targeting does not natively support the Hadamard gate, and that circuits need to be transformed using operator transformations. You also seem to be exploring using different backend systems by not using least busy. This error arises because the quantum hardware available on IBM's cloud has different restrictions on the allowed gate sets. To address this, you might need to use a different backend or apply compiler transformations.
Okay, so we have to apply the transpile.
Okay, I understand. It seems you've recognized that the Hadamard gate, H, is not directly supported by the backend you're using and that you need to apply a transpilation step. This is a crucial step in quantum computing as it adapts a quantum circuit to the specific constraints of the physical hardware. The images you've shared show that you are aware of the need to transpile the code before running it on the real hardware. You're on the right track.
I just took out the Hadamard gate transformation altogether.
Okay, I see. You've removed the Hadamard gate from your quantum circuit and are now just measuring the initial state of the qubit. It appears you're
Well, we
experimenting with
did apply an
simplifying
X
the
gate
circuit.
to it.
This is
So
okay. It
here's,
appears
you see the results there for the X gate. We have
okay.
1989011. Is that typical for the counts?
Yes, a measure. Okay, I understand you're asking if the measurement result you're seeing with 1989 counts for 0 and 11 for 1 is typical. In the context of quantum computing, and particularly for a simple circuit where you're just measuring the initial state of a qubit, then yes, this outcome is quite typical. When a qubit is initialized in the ground state 0 greater than, measuring it should ideally always return 0. However, there are some factors that introduce errors or noise into the system that can cause a small number of measurements to result in a 1. This is usually in the range of a few percent. So a result of 11 counts for 1 out of 1,000 measurements is within the expect range of noise.
All right. So that's pretty good. Um, I think we're just about done here. I want to try one last thing. I want to submit the counts to the ControlFlow agent and just ask it a basic question. I think we can try take the counts. Any suggestions there?
Okay, I understand that you're looking to incorporate the measurement counts into your control flow and want to submit those to the prompt. You're asking for suggestions on how to proceed. Based on the code, it appears that you have the counts and the counts underscore cloud variable. To include that in your prompt, you can use string formatting to insert it into the prompt message before you submit. For example, you could modify the line that creates the prompt to be Python prompt equals F. The counts from the cloud are counts underscore cloud. Please respond. Ooh. This will insert the values of the counts into your prompt. You can then submit the prompt using the response equals prompt underscore with underscore control underscore flow underscore LLM underscore QA underscore mathematics prompt function as you are doing currently.
I guess we'll ask that question. Oh, is the issue with the hardware because of the yeah, something went wrong? Got one more question to ask. We'll wrap it up here. Is the issue with the
Based on the provided images, it appears that the code and the user interface in the screenshots are related to quantum computing. The code snippets include aspects such as circuit creation and execution on IBM Quantum hardware using the Qiskit library, along with examples of retrieving and interpreting results. The presence of job IDs, circuit
so
diagrams,
here
and
we're
numerical
getting this qubit not supported because it's in superposition, and so for the IBM hardware, it only accepts what, like one classical bit and one quantum bit, or quantum qubit at a time.
Based,
Yeah, right here.
based on the provided images and your description, it appears you're observing a quantum computing setup where the IBM quantum hardware supports circuits with one quantum bit and one classical bit. The code example
Wow.
shown
So it looks like the ControlFlow agent is correct. That's using Gen AI, Google Gemini. It was correct because the result we got was what 1989 for the count, 10 and 11. Well, I guess it makes sense. It was able to determine what they were. So that's good. All right, that's it for the day. We'll uh we'll continue working with this in the future. Thanks for the lesson in Japanese.
Okay, based on the images provided, it appears you've successfully executed a quantum circuit on the
Okay,
IBM
bye bye now.
Quantum.
All right, that was
Farewell.
interesting. I guess I'm still talking to him. So we'll just stop that. All right, that was interesting. Started switching to Japanese and kind of calling me out on my lack of knowledge in quantum computing. So that was fun. Hope you learned something from this, and maybe you can try this in your workflow.